Hello everyone. Today we will talk about Unit 4 and we will discuss chemical compounds. If you remember from our last lecture, we talked about elements from the periodic table. So this chapter here will take it a step further to look into how those elements interact with each other to form chemical compounds. And that will evidently mean that we will be discussing chemical bonding and bond formation. Before we get into chemical compounds, we will talk about a classification of matter. And although we may have talked about classification of matter in our last lecture or a couple lectures ago, in terms of being solid, liquid, and a gas, but that's from the kinetic molecular theory perspective. Today we'll look at it from a chemical perspective, and how the chemical composition dictate how we classify matter. Once we finish with the classification of matter, we'll talk about chemical bonding. And I would like to really pay close attention to this because questions will be coming on this one in the first exam as well as in the cumulative exam, because this is really one of the core topics that we have in this course. So please pay close attention to this. So we'll talk about chemical bonding, and we'll be discussing two kind of bonding, the covalent and the ionic bond, and they are both different when it comes to chemical behaviors and chemical characteristics. So we'll talk about the covalent bond, the features of the covalent bond, and how the covalent bond actually take place on which elements are involved in forming this kind of bond. We will try to draw the covalent bond compounds as well as naming them. Once we finish with the covalent, we'll get ourselves into talking about the ionic compounds. We'll talk about the features of the ionic bonds and also naming the ionic compounds, because both are named in two different ways. In terms of classification of matter, we will talk about elements, and then once we understand elements, which is going to be a quick review from what we talked about the last lecture, we'll talk about compounds, pure substances, mixtures, and I will also try to explain how you guys are able to differentiate between each one of these, and how can you tell which one is element, which one is a pure substance, and which one is a compound. So let's talk about elements, and some of the stuff on this slide, or even on the couple of slides to come, it might look like a quick review from our last lecture, but that's okay. Let's get a quick refresher. So an element is a substance that cannot be chemically converted into a simpler form of substance, right? So if you remember that sketch that we had of the sodium chloride in water, and we talked about distillation, how can you separate the water from the salt, and then you break down the salt into the cations and the anions, and the water, break that as well. And we said once you reach the cationic level, anionic level, for example, for the sodium and for the chloride, you basically reach the elemental level, because you can't really simplify any further, right? So that's the elemental form. That's the elemental form, or the elemental classification of matter. It's the simplest form of substance that you cannot really chemically convert it into anything else. Okay. It's also a substance in which all of the atoms have the same number of protons. And if you again remember from our last lecture, we said every time we change the number of protons in the periodic table, what happens, we change also the identity of the element, right? If you look at the nitrogen, for example, it has 7 protons. If you add another proton and make it an 8 protons, you change the identity. It's no longer a nitrogen, it's an oxygen, right? So that's basically here what this statement means. That's an element. In order to be an element, everything in that matter, everything in that substance it must have the same number of protons. If you have a mixture of two substances that has two different number of protons, it's no longer an element, because you have two different elements combined together. Example of an element, diamond, because diamond consists of sheets of carbon atoms bonded together. There's no hydrogen, there's no water molecules, there's no oxygen, so we consider that an element. Likewise with gold. Helium in a birthday balloon, same thing. It exists in its elemental form. Okay. When it comes to element and how elements exist in nature, most of the element, they don't really exist in its elemental formation. Rather, they exist in a molecular shape. For example, if you look at the hydrogen never exists as a single hydrogen atom, but the hydrogen is actually bonded together as a molecule of two hydrogens through a covalent bonding, and we'll talk about this shortly. Neon, on the other hand, which is the element and noble gas from the last group on the periodic table. If you look at the farther right of the periodic table, that group of helium, neon, krypton, xenon, argon, so on and so forth, all these noble gases, those are the exception because they can actually exist in nature in the independent atomic formation as elemental formation. Okay? Silver, on the other hand, it's a group of assembly of silver atoms all bonded together, surrounded with electrons. So you're not going to find a silver atom sitting by itself. It just doesn't exist in nature. Neon, however, on the other hand, you can find it exists as a single atomic formation, compared to silver and hydrogen. So a few elements are found in elemental form in nature, and with that we mean just the noble gas in the periodic table. Others, they exist in a molecular formation, like the hydrogen, the oxygen, the nitrogen, so on and so forth. So it always exists as two atoms bonded together. Most of the substances we see consist of two or more elements. So when you have two or more elements bonded together, we call that as a compound. For example, is water. So water has a chemical formula of H2O. That gets us into talking about chemical formulas. And it is important for you to understand chemical formula and actually what chemical formula, what kind of information a chemical formula conveys to us. We will be using chemical formulas from this point moving forward when it comes to balancing chemical equations, when it comes to writing down chemical compounds and naming chemical compounds. So chemical formulas are pretty essential to our course, and I need to make sure that you guys are all able to write chemical formulas in a correct way. So what a chemical formula gives us, it gives us the name of the compounds as well as the number of atoms that element exists, the number of atoms of that element in that compound. So for instance, if you look at the water molecule, which has hydrogen, and you have a subscript of 2, that means I have 2 atoms of hydrogen versus 1 atom of oxygen in a molecule of water. So I have 2 hydrogen and I have 1 oxygen. This is the molecular formation, this is the molecular formula, or the chemical formula for water. It never changes. You're not going to find a chemical formula for water, H2O, in our textbook, and you'll find it as H3O, for example, in another textbook. It doesn't exist that way. This is the universal molecular formula for water. If you change the subscript adjacent to the atom, you are changing the identity of the compound. And I want to please keep that in mind, because I know some of you will make that mistake, especially when we go and we reach the level of chemical equation and balancing the chemical equations. So the number of the subscript here too means the number of hydrogen atoms in that molecule. If there is no number adjacent to that element, you should always assume the number is 1. Okay, let's look at the chemical formula for the saccharose, for example. This is a more complex compound, as you see, because I have carbon, hydrogen, and oxygen. And all these subscripts, it tells us how many number of atoms in a single molecule of a saccharose. So if you look at the carbon, that means I have 12 carbon. I have 12 carbon atoms in a molecule of a saccharose. I have 22 atoms of hydrogen, and I have 11 atoms of oxygen. So that's what a chemical formula tells us. It tells us there's carbon, there is hydrogen, there is oxygen. There's 12 of carbon, 22 of hydrogen, and 11 of oxygen. Okay? Now these atoms, or these elements in that specific compounds, they are connected, they are associated together through chemical bonds. So the atoms in a compound are joined together by special kinds of attraction called chemical bonding. Now what dictates what kind of chemical bonding do I have in that compounds? This is determined through the identity of those elements, because every element will have different elemental formation, different a different electron configuration, number of protons, number of neutrons, so on and so forth. All these will determine the kind of bonding that you will have. Because of the nature of these attractions, the atoms combine in a specific ratio that gives the compound their constant composition. What does this mean? The constant composition means that something like H2O will always exist as H2O because of because of the chemical characteristics of carbon, of oxygen and hydrogen. It always exists in water as H2O, so it has a constant composition that never changes. Now, a compound, on the other hand, is a substance that contains two or more elements. So when you have two different elements, two or more, bonded together, they form something known as a compound. So the atoms in a compound always combine in the same whole number ratio, just like how we looked at the water at the H2O. So it's 2 hydrogen and 1 oxygen. So in other words, you're not going to see something like 2 hydrogen and a half oxygen, or 2/3 of a hydrogen. It's always a whole number ratio. Same thing with with the sodium chloride, NaCl. So the formation and the structure of these compounds, it depends on the type of bonding that is being formed among the elements of the atoms of that compound. So, for example, if you look at the water, you will have 2 oxygens. You have 2 hydrogen and you have 1 oxygen centered in the middle. So you have 1 oxygen in the middle and you have 2 arms coming out of the oxygen. That basically describes the bonds that holds the hydrogen atoms. On the other hand, if you look at the sodium chloride, it exists as an assembly of sodium and chloride ions, always as 1-to-1 ratio. The water and the sodium chloride in this case are 2 different compounds with 2 different type of bonding. The structure of bonding, or the shape that these atoms take, it depends on what kind of bonding that is being formed. Okay, so going back to the compound, so the compound is a substance that contains 2 or more elements. So if you look at a substance in front of you, ask yourself, is it one or more? Is it one element or more than one element? If it is more than one element combined together, then it is a compound. A pure substance is something that has a constant composition. In other words, that you can describe it using a chemical formula. So if you have a substance in front of you and you're unsure if it is a compound or if it is a pure substance, ask yourself a question. Would I be able to describe what's in that beaker by a single chemical formula? If the answer is yes, then that is a pure substance. If the answer is no, then that's a mix. That is not a pure substance. Rather, it is a mixture of 2 different compounds mixed together. So if you look at the first beaker to the left here, when you have the 2 little bowls bonded together, so this is the hydrogen, this is the hydrogen molecule, where you have 2 hydrogen bonded together to form the elemental hydrogen. Now, my question would be, in order to describe this as a pure substance or not, now would I be able to describe this in a single chemical formula? The answer is yes. I can simply just write an H2. So as a result, this one is a pure substance. Let's look at the water molecule, or the beaker in the center. You have the oxygen and you have the 2 hydrogen. You have the oxygen, the big globe, and you have the 2 hydrogen on the side. Same question. Would I be able to describe the content of this beaker by a single chemical formula? The answer is yes, because I can only see H2O. I don't see anything else in there, right? So this is a single chemical formula, which is an H2O. So this makes it as a pure substance along with the hydrogen. Now, if I were to combine both content in beaker 1 and beaker 2 together, in other words, putting the hydrogen and the water together in the same container, now, would I be able to describe this by a single chemical formula? The answer is no, I can't, because it is a mixture of 2 substances, which is the water and the hydrogen. So it is no longer a pure substance. So in order to determine if it is a pure substance or not, try to describe it by a chemical formula. If you can, then it's a mixture. So this takes us to the next classification of matter, which is a mixture. So a mixture is a sample of a matter that contains two or more pure substances combined together and has a variable composition. In other words, it can't be controlled by one chemical formula because it varies. It depends on the composition, it depends on the condition, it depends on the how that mixture has been formed. So it changes and it's variable depending on the condition of that of the formation of that mixture. So that makes it a non-pure substance or a mixture of more than one pure substance. Again, it cannot be described by a single chemical formula. For example, the emission that comes out of the car, right? So it has water droplets. It has unbranched gasoline, a gasoline that runs through the engine and it has not really combusted, along with other gases. For example, like the carbon dioxide, the carbon monoxide, the nitrogen oxide gases, and so on and so forth. So in this case, the emission that is coming out of the car, there is no way for me to describe this by a chemical formula, which in this case it is a mixture of material. Okay. All right. Let's summarize everything together for a classification of matter. So we have the matter. It starts up here at the top. You're trying to classify what's in that beaker. Ask yourself a question. Does it have a constant composition? Can you describe it by a single formula? If the answer is no, then plain and simple, it's a mixture. It's a mixture and it's not a pure substance. Example for that is the coffee, right? Or the chocolate bar. The chocolate bar has the cocoa, has the milk, has the cream, has sugar, salt, nuts, so on and so forth. So it's a mixture of different substances being put together. Same thing with a coffee cup, right? It has the coffee, the creamer, the sugar, the water. So you can't really describe it by a chemical formula, so it's a mixture. If the answer is yes, you can describe it by a chemical formula. Ask yourself if it is a pure substance or not. Well, it is. No, it is going to be. I'm sorry. It is going to be a pure substance. Can it be described by a single symbol? If it can, then it's an element. If it cannot, then it's a compound. So it can be either water, or it can be either NaCl, or it could be any other compound, but not an element, not something that is coming straight from the periodic table. Okay? So if it's a pure substance, it can accept either a no as a compound or a yes as an element. In other words, both compounds and element are considered a pure substance in this case, right? But they are different in their chemical bonding and their chemical formation. Elements, they usually, compounds, they usually exist, form, or they are formed from different elements bonded together. Elements are not. Okay? Okay, let's put everything that we just talked about into real examples. So here on the left side, you have candy bar, you have H2O, you have the ocean, ocean water, oxygen, and the atmosphere. And on the right side, you have different classification of matter. You have the element, compound, or mixture. So first, let's do the candy bar. Ask yourself the question that I just mentioned earlier. Now, would I be able to describe this by a single chemical formula? Pretty sure the answer is no, because candy bar contains cream, like cocoa, sugar, salt, probably nuts. So it's a composition, it's a combination, a mixture of different substances being put together. So a candy bar would be a C. It's a mixture. Let's look at H2O. Same thing. Would I be able to describe water by a single chemical formula? Yes. So that would be a pure substance. Now, if it is a pure substance, it can accept either being an element or being a compound. Now, is it a compound or is it an element? Is it a group of elements bonded together or is it just a single element? Obviously, it is multiple elements forming the water molecule, which is 2 hydrogen and water. So 2 different elements, different bonded together, then it's a compound. The ocean water. It might seem at the first glance that it's the ocean water, so it's you can describe that by a chemical formula, but it's actually a mixture of different things together. Yes, water is the main composition or the main content of the ocean water, but you have other stuff in there. You have different salts. You have probably some sand in there. You have dirt. You have whales and fish and whatever marine life discharges. That's all mixed up all together in the ocean water. So the ocean water is actually a mixture because you can't really give it a chemical formula. Let's look at your oxygen. Is it a mixture or a pure material? It is a pure substance, correct? Because you can give it a chemical formula. It is an O2. Now the question is, it different elements or one element? No, it is one single element. It's only an oxygen atoms bonded together. Then that is an element. Okay, it's not a compound. It's an element. When it comes to the atmosphere has many different gases bonded. Many different gases exist. Some in large abundance, some in less abundance, but mainly it's a mixture of different gases that exist in the atmosphere. Right? It's either oxygen, nitrogen, hydrogen, a little bit of greenhouse gases like the methane, the carbon dioxide, and the nitrox gases, so on and so forth. So I don't think anybody can give any chemical formula to the atmosphere, right? So that makes it a mixture. So in the exam, I will be bringing this in the exam when it comes to classifying, substances. So I will give you different substances, and I expect you to really label them appropriately. Whatever is a mixture is a mixture. Whatever is a pure compound, element, a pure substance, element, or a compound, so on and so forth. So please try to listen to this, and if you have any questions, let me know. All right, let's talk about bonding. So now that we talked about compounds and elements from the classification of matter, let's take a deeper look into compounds and see how the atoms interact with each other and attracts each other, so compounds are formed. So in this case, we're talking about chemical bonding. We're going to discuss first covalent bonds, and then later on we'll talk about ionic bonding. But let's focus first on covalent bonds. So a covalent bond is defined as the link between atoms due to the sharing of two electrons. The key word that I would like you to pay attention to is sharing of two electrons and covalent bonds. So covalent bond formation, the main principle is the concept of sharing electrons. So electrons are not gained, electrons are not lost, rather it is shared by two atoms or by two nucleus. Okay? The covalent bond is also considered somewhat of a strong bond. In some cases, something like the methane, something like the carbon dioxide, the carbon monoxide, water, H2O, all these elements, the reason why we classify them as greenhouse gases, because they do hold somewhat of a strong bond. That's why they are known as greenhouse gases. Okay, because the bond between the carbon and the hydrogen, the bond between the oxygen and the hydrogen is really hard to break down, which make them, known as greenhouse gases. Okay, the bond forms between the atoms of two non-metallic elements. So if you remember when we talked and we looked at the periodic table, we said the periodic table is mostly divided into metals and nonmetals, and we said these folks on the right side of the periodic table, on the upper portion right here, all those guys, not the krypton, all those guys are considered nonmetals. Okay, so when we are talking about covalent bonds, and we are saying the covalent bonds forms between two non-metallic elements, that means all the covalent bonds forms between this group of element, right? Between the carbon, okay, let me clear this one out. Between the carbon, the nitrogen, the hydrogen, the phosphorus, the silicon, the bromine, and even the iodine. Okay, so those guys, they form the covalent bonds. So that's another feature of the covalent bond. This is also a good way for you to tell when you look at a compound and how do you determine if it is a covalent bond or a non-covalent bond or ionic bond. So you would look at the elements, you see if those elements are part of the non-metals group on the periodic table, that means it is a covalent bond. If it's otherwise, that means it's an ionic bond. So the bond forms between two non-metallic elements. So if you look at the hydrogen, for example, the hydrogen, it is a non-metal. So the hydrogen, if you go back to the periodic table, you see the color coding, it is a green. So it belongs to the green group, which is right here. So it is considered a non-metal. Okay, so the color codes on the periodic table actually means something. The water, the H2O, same thing. H2O, it is considered a covalent bond. The reason why? Because it is made of hydrogen, which is a nonmetal, and oxygen, which is also a nonmetal. Same thing with the oxygen. Carbon dioxide, same thing. It's also a covalent bond, and you can go for a long time trying to form all these compounds. That is considered a covalent bond compounds from any of those compounds in the non-metals in the non-metal section. So, for example, you can add to this group carbon monoxide. You can also add ammonia. You can also add methane, and the list goes on and on. So there's a long list of compounds that could be a covalent bond, as long as it is forming between two non-metals from the periodic table. So please, when we talked about the periodic table earlier, try to really listen carefully to these notes because knowing your metals, knowing your non-metals, it's really important to help you determine which is the covalent bond, which is the ionic bond, which later is going to help you when it comes to naming these compounds, and also writing the molecular formula by just reading the name. If you can't really determine if it is a covalent or it's an ionic bond, it's going to be very difficult, or you're not going to be able to answer those questions. Okay? All right. So let's talk more about the covalent bond. So one of the easiest compounds to look at when it comes to covalent bond is the hydrogen, right? The H2, because hydrogen is a nonmetal, so H2, it is considered a covalent bond. And if you take a picture of the covalent bond of the hydrogen atom, of the hydrogen molecule, you will see two clouds that represents the two electrons, and more electrons centered in the middle of these two clouds on both sides. So this is basically the nucleus of the hydrogen atom on both sides, and the electrons are shared somewhere in the middle. So there's a cloud that forms, and the electrons, as I said earlier, it's not gained, it's not lost. It is in the center between the two hydrogen atoms. So the two electrons in the hydrogen molecule are shared equally between the atoms. So the electrons are not going to the right. The electrons are not leaning to the right, nor leaning to the left. They are right in the center between the two nucleus. This sharing creates a covalent bond that holds the atoms together. So as the electrons are shared, the two nucleus and the electron cloud in the center really holds the hydrogen molecule together and give it that rigid structure. Okay. The covalent bond can also be defined and also divided into either a polar or non-polar covalent bond. So there are two types of covalent bonds. In a case when the electrons are shared equally between the two atoms, like the hydrogen, for example, the electrons are shared equally. It's not really leaning on either side. So there's so the electrons are evenly distributed between the two nucleus. The negative charge, in other words, it's right in the center. So there is no really partial charge on either side, on either ends of the bond, right? Because the electrons are positioned right here in the center. So neither sides have favorability when it comes to the negative charge. The negative charge is right in the center. Okay? So the bond in this case is called a non-polar covalent bond. The reason why, because we're not forming a polar situation, a polarized situation where you have one side that it's a positive and one side is a negative. The electron density is sharely distributed, is equally distributed on both sides, in the center, on both sides of the bond. So it is a non-polar covalent bond. A covalent bond, a non-polar covalent bond, always happens or takes place between atoms that are the same. What does that mean? Something like hydrogen. Both both atoms are the same, right? Because I have two hydrogen. So I have one hydrogen and I have one hydrogen. I have oxygen, O2, right? I have two oxygen. I have N2. Same thing. I have two nitrogens. So the covalent bond between these, the covalent bonds for similar compounds where you have two elements or two atoms of the same kind bonded together, it is considered a non-polar covalent bond. On the other hand, when one atom in the bond attracts electrons in a more stronger way than the other atom, that forms a polar situation. In this case, something like the hydrogen chloride, where you have the hydrogen and you have the chlorine, and the chlorine has more electron affinity, or something like electron negativity. That's something we also mentioned a lecture ago, right? So when the atom has more electron affinity, has a stronger power to grab on electrons, that would result in more electron density on either sides of the bonds. What that would result, it will result in a polarized bond where you have one side that it's partially negative, like in this case with a chlorine, okay, and you have one side that is partially positive. So the partially negative side, that's the side that has more electron density. On the other hand, the side that is positively or partially positively charged has less electron density. So there's more electron density on the element or on the atom that has higher electron negativity. So the electrons are no longer partially shared. However, there is more electron on one side and there is less electron density on the other side. If you want to look at it, it's just like similar to a tug of war, right? So if you have both sides, you have two men on both sides, they're both equal, and they're both they have the same power to grab on, and they both pull on each side. The rope basically is not going anywhere. It's center in the middle. However, if you change that balance and you have one side that has more power to grab more, you have one side, you have the other side, you have one side will basically be leaning to where more power exists. Okay, same concept here. If the atom has more electron affinity, more electron negativity, it will grab on more electron density. Now, keep in mind, we're still sharing electrons. We're not really losing completely of the electron. Electrons are not completely lost. So it is still shared. However, there is more electron on one side than the other. This is called a polar covalent bond. So we have two kind of bonds for the covalent bond. We have the polar and we have the nonpolar. The nonpolar, when we have two atoms of the same kind bonded together, something like the hydrogen, the oxygen, the nitrogen. And the polar, when we have two atoms different with electron negativity, different with electron affinity, that results in more electron density on one side than the other, resulting in a partial negative charge on one side and partial positive charge on the other side, the side that has less electron density. So when we are going to talk about drawing the covalent bonds, we're going to try to basically draw the molecular structure by looking at the compound and determine if it is a covalent bond or non-covalent bond. Now, if it is a covalent bond, we're going to try to count our electrons, later determine the central atom, and also draw all the other atoms that are connected to the central atom. But before we get into any of this, let's learn some concepts on how to draw the covalent bond. First and foremost, we are going to focus on valence electron. The valence electrons are basically the electrons on the outer shell of the atom when it comes to the electrons. That they are the last on the electron configuration. Those are the electrons that are involved in any electron interaction. The electrons that are closer to the atom on the first and second shell, for example, those are rarely involved, actually hardly involved at all with any chemical interaction or chemical bonding. It's the electrons on the outside that are either involved with sharing of electrons or donating or accepting electrons. So we're going to focus on the valence electrons. And when we say that, for example, if you're looking at the oxygen has 8 protons and of course 8 electrons in total, but we're not going to count the 8 electrons, the total 8 electrons when we are drawing our covalent bonds. Rather, we are going to focus on the valence electrons, and the valence electrons for oxygen is 6. So, well, first question would come, well, how would I know what is my number of valence electrons? Now, I think by the time we finish this course, everybody should be able to do electron configuration, and by that I mean by probably the first week of December. But before that, it's easy to tell what is the number of valence electron by just looking at the number of the group on the periodic table. Something like boron will have 3 valence electrons. Yes, it has 5 total number of electrons, but it has 3 valence electrons. This is the electrons we're going to count when we are trying to do our total number of electrons for the covalent bond drawing. Carbon will have 4 valence electrons. Nitrogen will have 5 valence electrons. Now phosphorus will have the same thing. Will have 5 valence electrons. The reason for that is because it belongs to the same group. Same thing with arsenic. Oxygen will have 6 valence electrons. Sulfur will have 6. Selenium will have 6, so on and so forth. Everything on the halides, fluorine, chlorine, bromine, and iodine, they all will have 7 valence electrons. And then you have the noble gases at the end, the helium, the neon, argon, krypton, and xenon. They all have 8 valence electrons in total, except obviously for the helium that has 2 valence electrons, okay? Now, let's try to do the electron dot symbol. It's also known as the Lewis structure. Now, we don't really address it as a Lewis structure. I don't think we will call it as such during this lecture, but we will later on in the course. We'll talk about it more in details, and we will talk about the Lewis structure. But in this case, it is the electron dot symbol. What we do is we use simply dots to represent valence electrons. So valence electrons are represented by dots. The way that we draw this, and I would like you to pay attention to this, we start drawing this by placing one dot representing a valence electron, a single valence electron. So if you're looking at the hydrogen will have 1 valence electron. So this will be the hydrogen. If you look at the helium will have 2 valence electrons. So this is the helium. Okay. Boron will have 3 valence electrons. So it will be 1, 2, 3. Now if you look, I'm going clockwise in this case, but it doesn't matter. You can go counterclockwise. You can, either go this side, or you can go on this side when you are trying to position your dot symbol, or the dots representing the valence electrons. Now, when it comes to the carbon, for example, which is right here, it has 4 valence electrons. So now I have filled all sides with dot symbol, right? So all sides are filled with single valence electron. And this is the most important rule when it comes to valence electron distribution using the dot symbol. You have to put the dots singles first, then you go back and couple. So every side, up and down, right and left, must have a single valence electron or a single dot before you start coupling and adding second electrons. For example, and I'll tell you one of the common mistakes that people will do. So if someone is writing the electron configuration, for example, for nitrogen, right, which is 5. So nitrogen will have 5 valence electrons. Now the correct electron configuration will be 1, 2, 3, 4, and that's a 5. And then you couple. People will make this common mistake. 1, 4, and 5. That's wrong. Always start with a single dot, single valence electrons on all sides, and then you go back and couple your electrons. Okay? And there is a reason for this. You will know the reason for this one by the end of the course, I promise. Okay? So let's look at the oxygen. The oxygen or the sulfur or the selenium, all folks, they would have the same electron configuration when it comes to the valence electrons. So we'll have one. So what I did with the oxygen, sorry, not hydrogen, not nitrogen, we're talking about oxygen. So we'll have 1, 2, 3. Actually, let's do this. Let me clear everything. So this is oxygen. I'm going to present it as an X so it's easier for you to see. 2, 3, 4. Now I've added all my singles. Now I'll go and couple. 5 and 6 electrons. So this is the valence electron configuration for oxygen. Okay. Fluorine, chlorine, and all the halogens on this group will have 7 electrons. Make sure that you add your singles, just like how I did with the oxygen. So something like fluorine, 1, 2, 3, 4, 5, 6, and that's my 7. Okay. Now when it comes to the noble gases, there's 8 electrons. Same thing, you'll add your 4 first, you get the idea. And then you couple with the other 4. So there is no really a set of rules that it's written in stone when it comes to how to place your paired electrons, your unpaired electrons, but just make sure that you pair your electrons once you have filled all sides, okay? Which means, like, if you look at something like fluorine or chlorine with 7 valence electrons, you can write it either way. You can have a single unpaired electron, below or on the right side or on the left. It doesn't really matter, as long as you follow the rule of putting single electrons and then you pair later. Same thing with 6 valence electrons, okay? So covalent bonds often form to pair unpaired electrons. That's basically the whole concept of covalent bond. So when you look at something like, for instance, something like chlorine or fluorine, and that would be a representation of chlorine or fluorine atom with 7 valence electron. You see there is a single non-paired electron right here. Covalent bonds are formed so unpaired electrons are paired. Each atom needs 8 electrons to be stable. So there is an octet rule that's well known in the chemical community, and with chemists, that every element or every atom must have 8 electrons in order to be stable. Okay. So the objective here for any atom across the periodic table is to get the golden number of 8 electrons at the end. So when you look at something like chlorine and fluorine, like this or earlier example, so chlorine, for instance, it's lacking 1 electron in order to reach the magic number of 8, correct? So what happens, fluorine is going to look for another atom that has another electron where that atom is willing to share that electron. So fluorine will be an 8, and the other atom will also reach the octet rule of 8. So it's basically a mutual benefits between the atoms, okay? So each atom needs 8 electrons to be stable. It's also known as the octet rule. So be familiar with this definition. Octet rule means 8 electrons. Now there are some exceptions. Hydrogen can only accept 2 electrons, and boron accepts 6 electrons. Now boron is a different kind of chemistry. There's actually the chemistry of boron, because it's such an oddball when it comes to chemical behaviors. Hydrogen, on the other hand, because it has only 1 orbital, which only accepts 2 electrons. So it doesn't really go beyond 2 electrons. So these are the only 2 exceptions: the boron and also the hydrogen. And you don't have to worry about the boron, because it's not gonna. I'm not gonna ask you questions about covalent bonds for boron, so you can take that out of your concerns. Okay. When it comes to the noble gases, those folks, they have the 8 valence electrons, right? If you go back to the periodic table that I just showed earlier, right? This is the noble gases right here. So those folks, they have the 8 magic number of 8 electrons, which evidently explains why the noble gases refuses to get involved in any chemical reactions or interactions. Well, rarely they do, but generally, noble gases doesn't really go into any chemical bonding or chemical reactions. Only maybe the xenon that some chemistry has been investigating the possibility of xenon reactivity. But in general, because it has 8 valence electrons, so there is no reason for the atom of the noble gas to look for another partner to pair electrons, because all the electrons, all the valence electron is pretty much occupied with 8 electrons. All the electrons are paired, so there is no reason to get involved in bonding. So it's so stable that they rarely undergo any chemical bonds or any chemical reactions. That's the reason why it's called the noble gases. So now that we talked about the dot structure and we can distribute our valence electrons, let's talk about the Lewis structure. And the Lewis structure, it's one of the really basic ways or basic methods of writing chemical structures and representing chemical formulas and chemical compounds. Okay, and it works really well when it comes to covalent bonds or simple covalent bonds forming between the nonmetals. Now, the Lewis structure, really fails in explaining certain bonds or certain chemical phenomena, but in this case, it really does very well and explains to us how the bonds are formed, what is the number of the valence electrons, and which one is the central atom, and which one has, more partial negative charge, and which one has the partial positive charge, so on and so forth. Okay. So for the Lewis structure, we use lines to represent the bonds. So anytime there is a line that draw between the center, between one atom and the other, that means it's a bond. So there's one line, that means it's a single bond. If there's 2 lines laid on top of each other, that means it's a double bond. If there is 3 lines, that means it's a triple bond, so on and so forth. Well, actually, triple bond. We don't go beyond that. Okay. And dots represent the electrons. So when we're talking about a chlorine, for example, which is what you see here above, so this is a chlorine, right? Or fluorine. This could be also fluorine or iodine. Okay, so this is a chlorine, and when we looked at the periodic table, chlorine has 7 valence electrons, and we did our valence electron distribution, and we found out there is one single lone pair on the chlorine atom. And likewise on the other chlorine atom. So we have 2 chlorine atoms with one single lone pair on each side. So what happens, these 2 lone pairs are willing to be centered right in the middle between these 2 atoms of chlorine to form a shared cloud of electrons between the 2 chlorine, which is also called a covalent bond. So in this case, if you do the count of the valence electrons, both atoms will have the golden number of 8 electrons on each of them, right? So there's 2, 4, 6 on the first chlorine, there's 2, 4, 6, and 8 on the second chlorine, and the bonds in the middle. So some people might really get confused by looking, for example, at this one. They say, well, 2, 4, 6, there's 6 electrons, there's 2, 4, 6, that is 6 electrons. Well, what happens to the octet rule? This is not stable. The line in the middle represents 2 electrons. So there is 2 electrons in the middle, but we substitute that by a single line indicating a single covalent bond between the 2 chlorine atoms. Okay? Now, a side question, now, is this a polar or non-polar covalent bond? This is a non-polar covalent bond. Why? Because chlorine and chlorine, obviously, they're the same. So the electron cloud will be centered in the middle, and there will be no partial negative charge nor a partial positive charge on either side, because they are basically equal in electronegativity or electron affinity to drag that electron. So the electrons is not leaning on either side, it is staying in the middle. Okay? Now, let's do some examples for Lewis structure drawing. So first, when we're trying to draw the Lewis structure, what we need to know our valence electron. That is your number one. That is your number one to do on your to-do list when you're trying to draw a Lewis structure. Okay, so number 1, I'll have to find my valence electrons. Okay, so what is my valence electrons? You will get that from the periodic table. So hydrogen has one valence electron. And chlorine, just because we mentioned chlorine so many times, we have been talking about chlorine. Chlorine has 7 valence electrons. So first what I will do, I'm going to write hydrogen, and it has 1 valence electron, right? Chlorine, on the other hand, has 7 valence electrons. So there's 1, 2, 3, 4, 5, 6, and 7. So this is the valence electron count. Where is my single count electrons? There is 1 single electron here. There is 1 single electron here. And we have to pair them. Remember, valence covalent bond is all about pairing electrons. So you have 1 electron from the hydrogen and 1 lone electron from the chlorine that's really looking for another electron to pair. So now here's the line between this electron and the chlorine electron. So now this will form a bond. So you have hydrogen, chlorine. Oh, sorry about that. Let's delete. So you have hydrogen, a line. We're going to represent that with a line, right? That's the bond. And you have your lone pairs. 2. So this is the Lewis structure for hydrogen chloride. Now let's do the ammonia Lewis structure. So what do I have? I have 3 hydrogen atoms, right? So I have hydrogen. This is hydrogen number 1. I have 1 electron. I have hydrogen number 2. That's 1 electron. All these single electrons, remember, it's looking for a second electron to pair. There is a second electron right here. Now let's look at my nitrogen. How many valence electrons I have for the nitrogen? Looking at the periodic table, I have 5 valence electrons. 2, and that's a 4. And here's my 5 electrons. So now nitrogen has 5 valence electrons. Now I'm going to try to look for every single electron, and I'm going to try lone electron. I'm going to try to pair it. I have this that needs to be paired. I have this that needs to be paired, right? Single electron on the nitrogen, single electron on the hydrogen. So these electrons now is going to try to pair and form bonds. What I need to do now, I just replace these arrows with single lines. So now I have the hydrogen, I have the nitrogen as my central atom. I have hydrogen right here. I have hydrogen. And I have hydrogen right here. These are my 2 electrons right here for the nitrogen. That is my electron on the hydrogen, my electron on the hydrogen. And this is my bond. So I'm going to replace these electrons with a bond, okay, with 2 electrons non-paired on the top. So at the end, your Lewis structure will look like this. Nitrogen, hydrogen, and 2 electrons for the nitrogen. So this is the Lewis structure for the ammonia. Okay? So here's some of the most common bonding patterns for nonmetals. Okay, and the reason why we're talking about nonmetals because we're focusing on covalent bonds, right? I don't expect you to memorize this chart right here, but this is something to share with you to kind of maybe you can learn some patterns and hopefully make things easier when you're trying to solve for Lewis structure. So something like hydrogen will always have a 1 bond. And I think we know at this point why it forms only 1 bond, because hydrogen has only 1 single electron and it's only willing to share that electron with another atom. So there is only 1 chance of forming a 1 single bond. Carbon has 4. Carbon forms 4 bond. The reason for that is because carbon has 4 valence electrons. Carbon needs 4 more electron in order to reach the octet rule, right? So remember, we need to reach the 8, the octet rule. So it needs 4 more electrons What does that mean, 4 more electrons? It means 4 more bonds in order to reach the octet rule. So carbon always forms 4 bonds. Nitrogen and phosphorus, 3 electrons, because it has 5 valence electrons, and it needs 3 more electrons to pair the non-paired electrons, right? All right, so nitrogen and phosphorus is the same. We have 5 electrons, 5 valence electrons, 1, 2, 3, 4, 5. So I have 3 electrons that are not paired, so 3 more bonds are needed, right? So we form 3 bonds with 2 lone pairs, nitrogen and phosphorus. Oxygen, sulfur, selenium, they act the same way. They behave similarly because, again, they belong to the same group, right? So it forms 2 bonds and it has 2 lone pairs. Why? Because if you look at the oxygen, for example, oxygen has 6 valence electrons. So something like the oxygen has 6 valence electrons. Here's my 1, 2, 3, 4, 5, and 6. I have 2 electrons that are non-paired. So I need 2 bonds in order to make it reach the octet rule. That makes 2 lone pairs. Lone pairs means the pairs that are not involved in the bond formation. Okay, so I have 2 bonds, and 2 lone pairs. Fluorine, chlorine, bromine, iodine. Those guys, they always form 1 bond with 3 lone pairs, right? Something like bromine, which has 7 valence electron, 1, 2, 3, 4, 5, 6, and 7. So I have 7 electrons, right? And I have 1 electron that it's requiring another electron in order to reach the octet rule, right? So bromine will form only 1 bond, and there is 6 other electrons that are non-paired. Now we can either say 6 electrons or 3 pairs, but that should, 3 pairs obviously means 6. Okay, so 2 pairs for oxygen, that means actually that is 4 non-bonding electrons. There's 2 non-bonding electrons for nitrogen and phosphorus, but we refer to them as pairs. Now, in some cases, as we talked earlier, a single line that represents 2 electrons are shared. In some cases, atoms can actually form a double bond and sometimes a triple bond. So when we say a double bond and every line represents 2 electrons, that makes it 4 electrons are shared. For example, like carbon dioxide. So carbon dioxide Lewis structure look like this. It's carbon and double bond O and double bond O. These 2 lines here represents 2 electrons. Every line represents 2 electrons. So that is 4 electrons are shared between the carbon and the hydrogen. In some cases, we actually even get to have a triple bond, which means 6 electrons. So something like the nitrogen, the N2. The Lewis structure for the nitrogen is N2,3, triple bond. So there is 6 electrons shared totally between the nitrogen. Okay, that is the 2 lone pairs here on the top, just to make things happy. Okay, so there is 6 electrons shared. So a double bond means 4 electrons. A single bond means 2 electrons. A double bond means 4 electrons. A triple means 6 electrons. So I will never ask you for questions to write a double or triple bond Lewis structure, unless if it is for an extra credit or something that I might bring in the 4th exam and again as an extra credit. So I don't want you to really spend so much time on this. I just want you to know and learn about the double and triple bonds, what they actually mean. If you are interested into getting an extra credit in the exam, by all means, try to read and learn more about the double and triple bond. But generally, I'm not going to be asking questions on these. Okay, so now let's try to name covalent compounds.